Yeah, so I have actually talked about these things in the past in this quantum space-time, but this is something. Yeah, I mean it is just a development of that. So let me start by saying that in flat space holography, the dual field theory has to compute the S matrix. Now, in flat space, the asymptotic symmetries are infinite dimensional, and they act on the S matrix and the word identities for these symmetries are the soft theorems, which we know from the work of this. So now the thing is that what we will talk about in this seminar is basically how to use some of these infinite dimensional asymptotic symmetries to solve for the scattering and amplitudes in some simple examples. Okay. So now this is basically we know from our experience with the two-dimensional conformal field theory that if you have infinite dimensional symmetries, then it's not always necessary to know the Lagrangian description to solve that. And the thing is that in this case, we will see that for some classes of scattering amplitudes or S matrix in flat space, one can do the same type of thing. Okay. So now.
Sorry, Shamik, can I ask a basic question? I know embarrassingly little about all these developments, so please forgive me.
Yeah,
is there even if you don't mind, you can answer later also privately. Is there even a Lagrangian description known for the problem you're discussing?
No. So that's what I said actually, that we don't know what the Lagrangian description is, or even I think it is better to say that we don't even know whether a dual quote-unquote field theory actually exists in asymptotically flat space. But the thing is that since we have this infinite dimensional asymptotic symmetries, we may hope to solve some simple subsectors of this quote-unquote dual field theory.
Yes.
I understand that. Yes. Yeah, so it is like the two-dimensional conformal field theory, for some values of the central charge, we know that we can solve the for the correlation functions. So it's in that sense actually.
I understand. Thank you.
Yeah, so it is some simple example actually we'll see. It's simple, but it's non-trivial actually. So that we'll see as I go along.
Okay, thank you.
Yeah.
Sorry to interrupt. What about the boundary theories? Do you call it a local theory? Is it in any sense local or not?
Well, so the local, well, I mean, you have to really define what you mean by local. But what we will see that it is the OP actually exists. So that thing is there.
And do you have a complete set of operators which closes under OP expansion?
Yeah. Yes. So that we have.
Okay.
So that I will see. So the basic thing is that we have there are two facts. First of all, this that you have this infinite dimensional asymptotic symmetries, and you have the OP So those two things are there, and we know that if we have these two things, then we can say a lot of things actually. I mean just from our experience with the two-dimensional conformal field theory.
Right.
Yeah, so it is not just this infinite dimensional asymptotic symmetry. So this is first, and the second thing is that there is a notion of OP, which which I'll talk about actually.
Excuse me, are you assuming super rotations also in this?
So the in the subleading software, so the super rotation will not directly actually play any role in this case for the class of S matrix that I'll talk about, but it is more general. So now actually the super, so it has been known for some time, I think for the last 2-3 years, that it is not just super rotation, but you also have the diff S2, right? So that is also an asymptotic symmetry, and singular diff S2, so they actually play a role here. So that I will make clear once.
Okay, all right, thank you.
Yeah. Okay, so these. Okay, so now what we can do is that so this job that if we want to compute the scattering of amplitude from these things, then that job is actually greatly simplified if we go from the Fock space to the celestial sphere by making transformation, which is an integral transformation of this form, where this epsilon is ±1 depending on whether this A is an outgoing or incoming particle, and these things are so this integral transformation, so that holds only for the massless fields. So you can do the same thing for a massive field, but we will not talk about that because yeah, so that's not the thing that we will talk about in this year. Now in this case, so this sigma is the helicity of the massless particle, and this the momentum has been parameterized as p mu equal to omega times this 1 plus z bar, z plus z bar, and all these things. And in this case, the z and z bar, they are the coordinates of the celestial sphere. Now the good thing about this integral transformation is that this particular field which you have here, this phi h bar, z bar, so that's a primary operator with scattering dimensions h and h bar. So these are the standard expression from the two-dimensional conformal field theory. So h is delta plus sigma by 2, and h bar is delta minus sigma by 2, and this delta is the one which appears in the integral transformation, and this phi h bar z bar, so that's a primary with scattering dimension h bar under the SL2C, which acts on the sphere as the global conformal group. So these fields are the ones that that we will be working with, and so this delta is the scattering dimension which we take to be complex, and we also treat these z and z bar as independent complex numbers.
Sorry, Shamik.
Hi. Yeah.
if the real part of delta is large enough, typically it looks to me like the right hand side of this equation will be typically divergent. Is that right? Or
yeah, actually we'll see. So this is of course formal transformation. Now if I go to the next slide, so this is the integral transformation which acts on the S matrix. Now actually now depending on what your S matrix is, this integral can blow up. Okay, and the point is that I have not talked about that particular type of regularization that I use. So what I will do is that I will insert a phase factor, which is like e to the power I omega u, and then that actually solves this thing.
I see. Is this equivalent to working with small real delta and analytically continuing to large real delta?
You can think in that way. Yes.
I see. Thank you.
Yes. Yes. Yeah. So I have. So I will not talk about that part actually. So I have. Yeah. So I talked about it long ago in one of these quantum space time. So you can do slightly different integral transformation, which actually cures this thing. And but the thing is that, yeah, so you can just take my word for it that it actually yeah. And the other point is that, as you said, if I take, I mean, this is true in the sense of analytic continuation. Yeah. So
is there an inverse transform also?
Yeah, this inverse transform of course exists. Yeah. So you choose some contour for this. So you have to integrate over this delta. You have to choose some contour, and you can do it actually. Yeah.
Sorry, I have one more sort of slightly vague question.
Yeah. Yeah.
Integrating over these omegas, I would have thought of as making a wave. If it was a more reasonable kind of envelope function, I would have thought of as making a wave packet in time. Right, because
yeah.
Okay, but this very singular kind of omega, which blows up at large omega, what is the? I mean, what physically are you doing? You had some words in the last transparency saying this amounts to transforming to the celestial sphere. Sorry, could you explain that? I mean, why is it a strange thing?
Oh, so this integral that why it goes to celestial sphere is because of this particular form. So if you write p mu, so this thing is massless. So you can see that this zz bar is essentially the direction in which the massless particle moves.
But that's true both on the left-hand side and right-hand side of equation 1.
Yes.
The transform is over this omega. Why are we doing this funny omega transform?
Well, omega transformation, that is because of this equation. So these fields now transform like a conformal field theory correlation function.
Okay. And apart from this formal property, is there a physical way of thinking of this integral transform? It's a vague question, and we can just
physical way.
Okay, thank you. We can talk about it later. Sorry, Shamik. Sorry for interrupting.
Yeah, actually, no. I mean, that's a guy. Yeah. This is well. Just let me think of actually, you can do some group theory here. So I will. So I thought of skipping that whole part because the thing is that I will talk about something which is not really. Yeah. So I think from the group theory point of view, you can actually. Yeah, I mean, it makes more sense actually. So
sorry.
Yeah, so actually I did that, but I have actually not. Yeah, so I will not be talking about that because I mean that's a separate thing actually. So for this talk, I am just thinking of this integral transform as something which is like given to me actually. So yeah, so physically, I think the group theory. So you can look at the representations of the SL2C, and that's how you get this thing actually.
Okay, thank you.
So, yeah, so this integral transform, you can also get it in that way. So that is more physical way of doing this thing. So basically what you are doing is that you want to show the way you are basically diagonalizing the boosts. So that's what you are doing. Instead of the p mu's, so now you want to diagonalize the boost actually. So if you do that, then you basically get these fields, this phi zz bar, phi hh bar, zz bar.
Thank you.
Yeah, but we can talk about it more actually at the end probably. Is that fine?
Of course, it's fine. Please go.
Okay.
You know, Shamik, you have to go on, and I'm totally ignorant, but just to ask you, is the inverse Mellin, is the inverse Mellin transform sort of defined also? Because in a sense, you may say what you're going to do, compute your product of the correlators, the phi's,
right.
using the nice properties, and then if the inverse is well defined, then you'll obtain the S matrix element, which will have correct properties.
Yeah. So this inverse can be done actually. So I think this is just some choice of contour in the delta plane actually.
Okay. Yeah, go on. Thank you. I'll learn more from you.
Shamik, I have a very remedial question. Yeah, sorry.
Yeah, go ahead.
Yeah, I have a very remedial question. These deltas that the primaries that you are showing. So let's consider the very heavy primaries, the asymptotic ones. And do they satisfy these Cardi-like formulas for density of states?
Okay. So those things are not known actually. So first of all, so let me just go ahead with this. So those things are not, I mean, at least I don't know.
Okay, that's fine.
I'll just
more information. Okay.
Yeah.
Shamik, one question.
Yeah.
So where does it go into your equations that these S matrices are on-shell observables?
So this is how I write this p mu, right? Oh, what happened?
You already solved for the on-shell condition.
Yeah. So this omega zz bar. So those are the three. So in terms of which you write the p mu, and then you integrate out the omega. So that's how. Yeah.
It's at the
and
moment.
One more.
Sorry, labeled by angles and energy, but not a radial momentum.
Yeah. So that is
right.
Yes.
So one more question. So
yeah.
The way you're transforming, you are getting a phi for every delta, any delta you want.
Yeah. So right. Yes.
So that the spectrum, I mean, if one were to think of this phi to be part of some conformal theory or something, then there are, in continuous spectrum in delta or something like that.
These will have this continuous scaling dimension. But things like if there is an Hilbert space interpretation or these things, so those things are not completely clear actually. But But the thing is that, I mean, we'll see that they more or less work like two-dimensional conformal field theories with some extra infinite dimensional symmetries. Yeah, but those like this Fox, like the if you want to count state, I think state counting does not. I mean, at this point, it does not make much sense because you have infinite number of states if you say that way. Yeah. So those questions are there, but I don't know the answer actually.
One more question, sorry.
Yeah.
So one can people have been looking at scattering in ADS being equal to CFT correlators, and in the flat space limit, I would have expected that this picture would become very similar to that picture, right?
Yeah. So
and there, of course, we have correspondence that delta becomes the mass of the particle. But here, the delta is being transformed.
Yeah, so these are all
So,
mass. Yeah, so in this case, delta is just a continuous here. It has nothing to do with, so far, it has nothing to do with the mass actually of the bulk field, say.
okay.
So is that okay?
Yeah.
Yeah. So let me just go ahead with this thing. So you can look at, so you can do this integral transformation on the S matrix, and then you get this calculation function of this phi, these conformal primary fields, this phi h bar z bar. And the good thing about this is that this transforms. So if you make an SL2C transformation on the sphere, then this is how the calculation function will transform, which is the standard way. And then, so in this talk, so these calculation functions are the main object of interest in this talk. And let's now go to the thing that what kind of word identities are
Shamik, can I ask a question?
Yeah, yes.
So so in equation equation 3, in equation 3,
right,
so this omega integral is along the real line, right?
Real line, yeah.
And delta, you said in the previous page that delta is a complex number.
Yeah.
So, but they are conjugate to each other, I presume. So I guess.
Yeah. Well,
I guess that
so it is. The thing is that it is in the sense of analytic continuation, in the sense that so it's a complex number. So it is actually, you start with deltas of the form like d by 2 plus I lambda. So it has actually one
I see.
one actually. But then the point is that once you have an S matrix, you can do this integral, and then at the end of the day, after doing the integral, you can analytically continue. So that's what I meant actually.
Okay, all right.
But to start with, so this delta, the imaginary, the real part of delta is actually fixed in terms of the dimension of the sphere. So it is like d by 2 plus I lambda.
Okay, right.
So you have just one, yeah. So that is not easy actually. So yeah, right. Yeah. So that's the thing. So is that fine?
Yes. Thank you. Thanks
okay.
a lot.
Yeah. So now let me move on to the next part, which is the word identity part. So now let's write down the word identity. So we know that that we have this soft factorizations. So this is the subleading soft factorization. And the thing is that we have, so this is the subleading soft factorization on the sphere, because that's where all these fields, these phi's are defined. And we have defined this S plus 1 ZZ bar by this in this way. And this is the subleading conformally soft graviton, and this G plus delta ZZ bar. So that's the positive helicity graviton with scaling dimension delta. So in this case, the H and H bar are like delta plus 2 by 2 and delta minus 2 by 2. And the thing is that this S1 plus ZZ bar, so that's a primary with scaling dimensions 1 and minus 1. Okay, so now what we'll do next is that we want to recast this thing in the form of a word identity, like which is more clear. So this almost has that form, but it is just easier to write it in this way. So what we do is that we take this this s plus 1 z z bar and we extend this in powers of z bar. Okay, so we have this.
Shamik, in your last slide, you showed this operator s as dimension 1 and -1, right? So you are allowing negative dimensions as well, unlike CFTs, usual.
Yeah. So it is not just negative. So you can have complex scaling dimension also.
So there is no unitarity constraint or things like that in this. There's no unitarity constraint.
Unitarity, okay, so the point is that it turns out that if you take delta to be of the form d by 2 plus I lambda, where d is the dimension of the sphere, so in that case it is a unitary theory, so that one can say. In fact, that d by 2 plus I lambda, that particular form is, you can fix it in that way also. But the thing is that now, as I said, so once we do this integral, so once I take an S matrix and do this integral, so at the end of the day, I can analytically continue in delta, like we can. I mean, yeah. So yeah.
And sorry, Shamik,
in
that equation for the subleading soft graviton theorem, the scaling dimension hi and hi bar are, you're taking n of them, but their exact values are not specified.
No. So yeah, so that thing is not fixed. So you can take whatever you want actually.
I see. So for any value, you get something which is connected to the subleading soft graviton.
Yeah.
Okay, I see. Thank you.
Yeah.
Excuse me, I'm kind of confused about the logic here. Are you saying that we knew the theorem, soft theorem first, and then
you do this integral transform?
Okay, and then cast it in this form.
Yeah.
And then you recognize by comparison that you need to S1 plus is what you're calling subleading conformally soft graviton. Okay.
Yeah.
Okay. All right.
Right. Yeah. So this equation is obtained. So we know what it looks like in the Fock space, and then you do this integral. Then you do this integral transformation, and then that's what you get actually. Yeah. So that is essentially what is being done here. Now the thing is that in order to recast this in a more useful form actually, so this is more or less has the form of a word identity. But the thing is that what we do now is that we expand this S1 plus ZZ bar like this. So we have, so in powers of Z bar, so we expand this in powers of Z bar, because if you look at the right hand side of this soft theorem, you can see that you have only Z bar in the Z bar minus Z bar k squared. So that squared. So this expansion will stop at Z bar square, and you get three contents which are like J1Z, J0Z, and J minus 1Z. And now if you take this expansion and substitute it back in this subleading soft theorem, what you get is these three word identities, and you can easily recognize them as the word identities for the SL2C bar. In particular, so if you look at the word identities, so these word identities, so they are equivalent to the global SL2C bar transformation of this form. So the first one, say for example, if you look at J1Z, and if you look at the residue at the pole Z equal to ZK, say, then the transformation is just this. So that acts on phi, which is, is the standard thing, that L1 bar acting on phi. And similarly, delta naught is L0 bar, and delta minus 1 is L bar minus 1 acting on phi. Okay. So now what we do is that I can define the modes, the JAN, and which generate the local SL2C bar transformations of this form. and these modes satisfy the standard algebra of the form that JAM computed at JBN is equal to A minus B times JA plus B by M plus N, where AB is 0 and plus minus 1, and M and N are integers. So this,
and Shamik, sorry to keep interrupting.
No,
please
ahead,
excuse me. Just to get the basic picture, you're computing this is related to computing a S matrix for, say, n plus 1 gravitons, where one graviton becomes
one of them soft.
One of them soft. The others can have whatever momentum. That corresponds to your n operators having whatever h's and h bars.
Absolutely.
That is the deltas. Okay, I got that. And okay, so that's how this map goes. Okay.
Yeah.
Thank you.
Absolutely.
Thank you.
So that's it.
Thank you.
Yeah. So this is just the standard subleading soft theorem, but we have done this integral transformation to go to the sphere. So that's the change.
Sorry, and the fact that these correlators were analytic in Z, that came automatically somehow.
So this, you mean the subleading soft here? The subleading soft theorem?
Yeah, you had this expansion of these J's. And they were somehow analytic in Z, right?
Well, it's analytic. Yeah. So the point is that I have written it in the form, it's an analytic in Z. So you can write SE in this. But the thing is that this has a slight Z bar dependence in the sense that I could have expanded around some points, say Z bar equal to Z, some Z bar not.
Okay. You're doing a Taylor expansion in Z bar. And then the coefficient of that are by definition analytic.
Yeah.
Thank you.
I see.
And so the fact that you're talking about SL2C bar is because you're taking S1 plus. So if you were to take S1 minus, then you would be SL2C.
Yeah.
Okay. All right. Thanks.
So this SL2C bar I call because just this. Yeah. So that comes from the S1 plus. Then if you take the S1 minus, then you get the SL2C. And it is I call it the SL2C bar coherent algebra because the these word identities are equivalent to the global transformations of this form. So that's why, I mean, you are just making it. You are just making part of this Lorentz group local. So that's
just one more thing you said earlier, and so soft graviton, and what is the conformal soft graviton? So why is that?
Yeah, conformal soft graviton is essentially this object. So you write S1 plus ZZ bar equal to limit delta going to 0 delta times G plus delta. Now, because we call it the conformally soft, because the point is that on the sphere, since you have already integrated out the energy, so you don't have any notion of soft. But it turns out that the notion of softness is now in terms of this scaling dimension. So that's why we call it the. I call this is the that's why it is called the conformally soft.
Okay, thanks.
Yeah.
So, Shamik, just one question.
Yeah.
So
I
now,
get some extra time at the end, right? Because it's all okay. Yeah. Yeah.
You can easily go till 1 o'clock, Shamik, and probably even more.
Thank you. No, I know that actually because all this quantum space time.
Yeah, you know. Yeah, you know that.
Okay. Yeah. Just go ahead.
So if you have a particle, in the flat space, you would label its representation by Casimirs of the Poincare group, in particular by mass.
Right.
Now that particle is being transformed into this conformal primary or something, let's say phi, right?
Yeah.
And now that as a conformal primary, you could compute the Casimir of that is in terms of delta.
Right.
So if you want a map from this particular representation of the Poincare group to that particular representation, it's natural that the two Casimirs be related.
Yeah, so
Right?
this is
but
not
here they are transformed. So
yeah, so one point is that this is not really a representation of the full Poincare group. So this is a representation of the SL2C. Because the point, I mean, you know.
Okay, only the Lorentz. So you swap your Casimir for the translations to the.
Yeah, I think that, yeah, you know this better than me. So, yeah. So this unitary principle is representation of the ASL2C.
Okay. Thank you.
Yeah, so that's how it starts. But the thing is that at the end of the day, once you compute this integral transform, you can do an analytic continuation, and that is actually an important thing to do actually. So we'll see actually why it is like that. Yeah. So let me. So this is there any question? So we have this SL2. So we saw that this subleading soft Graviton theorem is the same as the SL2C bar. Algebra of this form. And now, so let me talk about some of its interpretation, possible interpretation. Sorry, so this is so you can so this is actually a possible interpretation in terms of the diffeomorphisms of the sphere. Is that you can think of this SL2C bar algebra, because for the last 2-3 years it is known that it is not just the super rotation, but you can also have the d phase 2, but you see that it is actually the singular d phase 2s which actually play a role. So let's look at consider diffeomorphisms of the plane of this form, like where z goes to z and z bar goes to z bar plus az plus bz z bar plus cz z bar square, where these functions, these az, bz, and cz, they can have poles. Okay. Now the thing is that what we can do is that we can choose a basis of vector fields which generate this diffeomorphism, and they are of this form. So what we have done is we have just done a mode expansion of this az, bz, and cz, and then you get vector fields of this form, and they have the same algebra. That so their algebra is the same as the SL2C bar algebra that you saw. Now this is the classical algebra, but it turns out that this is the one which will be important for our case actually. Okay, so this is essentially that. So if you want to think of this as an asymptotic symmetry group, then I think that's the way to think about it. The only difference is that the d phase 2, you also have to include the singular d phase 2s, and those singularities have this form, that I mean they are of this form actually. Okay. So now let me go to this thing, which is the important thing. So now we know that we have got this all these word identities, and what we now want to do is that. So this is,
sorry to interrupt, Shamik. Correct?
Yeah.
These J's came originally from inserting sort of, roughly speaking, soft gravitons, right?
Exactly. Yes. So that's what we did actually. Yeah.
Right. Now for any one direction, there's exactly one soft graviton.
One soft graviton, one or well, I mean you have basically two in the sense.
The helicities you're saying, but I thought there was one different. Okay, maybe two.
Yeah.
You're getting now an infinite number of insertions in any direction. All these modes of z and z, these analytic modes of jn's. So I was wondering, those they came from scattering gravitons, but those are not themselves S matrices of gravitons, are they?
Sorry. No. Just go ahead. Yeah.
What combination of these? What do you do with these J's to get the original soft graviton insertion exactly?
No, actually, where are my slides? Just. Okay. No. Just if you repeat, can
it's probably a very foolish question, but let me ask anyway.
No. Yeah. Just.
Okay. At any given direction, you could insert a soft graviton into your S matrix.
Yeah.
That's one or maybe two things you can do. Whereas here now you've got an infinite number of things you can do.
Yeah,
right?
so that is because of this, because of the fact that these J's, they satisfy these word identities.
So if I put J0 5 minus 5 on this correlator, is that quantity, does that have an interpretation in terms of inserting some sort of graviton?
Yeah, so that's what I will just say now actually. Just that is exactly the thing I will say now. So that's where this thing comes actually. So I need the OP between this S1 plus ZZ bar and primary phi. So what we do is that we have this this subleading soft theorem or the word identity, and suppose I want the OP between S1 plus ZZ bar and say phi H1 bar Z1 bar. Okay. So now, so we do the standard thing. So we just expand the right hand side of this word identity in powers of Z minus Z1 and Z bar. So now ZZ bar goes to Z1 bar, and you expand the right hand side of the subleading soft theorem in powers of Z minus Z1 and Z bar minus Z bar 1. And that expansion in powers of Z minus Z1 and Z bar minus Z1 bar can be written in this form, where so these are the things that Cachazo was actually saying, that so now I have this J1 minus P, J0 minus P, and J minus 1 minus P, and there are some operators, and they have this particular form. And we have also introduced this particular notation that J1 minus P acting on phi H1 bar Z1 bar. So this is essentially the insertion of the SL2C bar Carpenter algebra descendant inside an S matrix, and that is given by this. So is that
just to check, I'm maybe very confused, but the minus J minus dependence, that's like Fourier transforming the dependence on the sphere? Jn. So you've got three guys on top and an infinite number of modes at the bottom. And that's like trading for the angular dependence of the sphere. Is this right?
Yeah, sphere or the plane. So, or yeah, so now actually, yes. So that is essentially the
Fourier transform. Okay, excellent. Yeah. And why did you, and from the point of view, so I understand that infinity, that's just the spherical harmonics on the sphere.
Yeah, you can.
Okay.
Yeah. And actually, I'm thinking in terms of the plane. So
sure.
Series cylinder to the plane. So in that way, actually.
Okay, and but why these three modes that you had on top? Can I understand that from the point of view of soft gravitons? Why did I have 1, 2, 3?
Three modes.
The SL2C indices.
So that's the Z bar expansion of these.
Okay. Okay, thanks. Please go on. I'll ask you.
Yeah, so that's the Z bar expansion of this. And once you actually substitute this in this soft theorem, and if you compare the equal powers of z bar on both sides, then of course what you get is this.
Okay, okay, I understand. Thank you.
Yeah, so that's how actually we got this thing. So is that does that answer your question?
Just to be completely clear, there is no further in the, all of these J's are producing some soft gravitons, some linear combination of soft gravitons, some directions of the sphere. This is right?
Yeah. Yes, I mean you can think in that way, and I think this this thing actually answers your question, that these are the descendants, the J descendants of phi. So
inserting soft gravitons is actually going to descendants of the hard gravitons.
Yeah. Yes.
Thank you. And all of these these SL2C generators are producing only soft gravitons.
Yeah, the descendants of the hard ones actually.
Hard ones are all hard gravitons plus more soft gravitons.
Well, soft, yeah, you can think of, hard and the descendants of hards. But you can think of this as raised by soft, yeah.
Thank you.
Yeah, I think that. But the thing is that at the level of algebra, so that's how the asymmetrics of these raised hard things are look like actually. So that we know that, I mean, how it looks like, and that actually essentially comes from by expanding the right hand side of the subleading soft graviton theorem. So that's what we have. So these things are important because that is what we will need when we construct the OP. Okay. Okay, so now, so these are the SL2C bar coherent algebra descendants, and now let me look at this. So now what I can do is that it is just useful to write this in terms of the OP between this S1 plus ZZ bar and this phi H1 bar, Z1 bar, and we can write it in the standard form. And the thing is that since this S1 plus ZZ bar is given by this expression, the OP between the S1 plus ZZ bar and phi H1 bar, Z1 bar can also be written in this form. What I mean is that if I compute the OP of the G plus delta ZZ bar and phi H1 bar, Z1 bar, and then if I take the subleading conformal soft limit of that, which is this, then what I will get is essentially this one, which is completely fixed in terms of the subleading soft graviton theorem. Okay, so now yeah, so now actually we can do some formal thing in the sense that this OP, if I look at this OP, then this OP is equivalent to these relations, that is JAP acting on phi HH bar. So this JAP will kill this primary field phi HH bar for all P greater than or equal to 1. And we also have, on top of this, we also have these standard ones which are satisfied by this phi HH bar, which is that J1 naught, which is L bar 1, that also kills the state phi HH bar, and this J naught, which is L naught bar, so that acting on phi HH bar gives me H bar times phi HH bar. So these they define the SL2C bar coherent algebra primary phi HH bar. Okay, so these things we will use later on actually. Okay, so now we can do the same thing with the leading soft graviton, and that has these forms. So I have written S naught plus ZZ bar, so that when it is inserted inside the S matrix, and if you write it on the sphere, then or on the plane, I'm not really working on the sphere, in terms of the planar coordinates. So this is the form of the leading soft theorems, and these are some things like these PKs. So what does this PK do? So if it acts on a field like phi h bar, it just increases the scaling dimension by 1, but it will not change the spin. So h and h bar, they increase by half. Okay, and these epsilons are plus minus 1 for an outgoing or incoming particle. Now this S plus naught ZZ bar, so that's the leading conformally soft graviton, and that is given by this. So it is just like this expression, just like this, but now delta actually goes to 1, so that's the leading conformally soft graviton which you have, and it is also a primary with weight 3.5 and minus half. Okay, now we can do the same thing. So we can expand this S plus naught ZZ bar in powers of Z bar, and since on the right hand side we have a single power of Z bar, so this expansion actually stops at Z bar, and we have two coefficients here, which I call P0Z and P minus 1Z. And if I insert them, so if I now substitute it back into this soft theorem, what I get is this, the correlation function of P0Z and P minus 1Z, and they have this form, and these and they are equivalent to the global space-time translations which act on this phi h bar in this way. And now you can see that the point is that if I just so they increase the scaling, so global space-time translation, so that increases the scaling dimension h and h bar by half and half. So the point is that, so that's why if I fix the delta to be of the form d by 2 plus I lambda, then I don't really get a representation of the full Poincare group, because if I start with d by 2 plus I lambda, and once I act with a global space-time translation, I'll get d by 2 plus 1 plus I lambda. And that's why it is good to think in terms of in terms of analytically continued fields or amplitudes. Okay, so this is all here. So now we can just define the modes of these P0 and P minus 1, and they give rise to these super translations. Okay, and we also have the, so they form an abelian algebra of this form. Okay, so now we have to do basically the same thing. We can compute the OPE between this leading conformally soft graviton, this S plus naught ZZ bar and phi H1 bar. So you can do the same thing. You can expand the right hand side of this soft theorem in powers of Z minus Z1 and Z bar minus Z bar 1. And you can write the OPE in this form, where now P minus A naught phi H bar and P minus A minus 1 phi H bar are the super translation descendants when A is greater than equal to 2. Okay, so this is, so we have played the same game actually as in the case of the SL2C bar. Okay, now we can also have the insertion of the super translation descendants, and their insertion in the S matrix is given by this. Also, this has this form where these P's are the same. They act on phi H bar and increase the scaling dimension H bar by half and half. Okay, so that's what we get. Now, these are the important ones which will be used when you compute to extract the OP from the amplitude. Okay.
Can I ask a question here?
Yeah. Please go ahead.
So from this leading part, you got the commutation relations for these P's, right? And they're
yes.
Boolean. And then from the subleading part, you got the commutations for J's, for the currents, and the corresponding word identity, or I mean the subleading from the subleading word identity.
Right.
Now, what about the commutations of P's and J's?
Yeah, so that's what.
Where are they going to come from?
Yeah, so they are just given by this actually. So you can get it from the multiple soft graviton, or if what you can do is that you know how they act on these fields, and you can compute the classical algebra, and that is just given by this. So they actually what is what is useful and interesting is that these super translation and the SL2C bar coherent algebra, they actually form a closed algebra of this form. So that's a useful fact, I mean, which we need actually.
Sorry, I didn't get the first part. You said you could get it from what kind of identity?
The multiple soft graviton.
Okay.
So you can take you can make two plus helicity graviton soft, and then that has a corresponding factorization, and that can lead to this also.
Okay. All right. Thank you.
So it is like J, and then, or it should be like JP. So you make one of them leading soft, another one subleading soft, and that gives you this thing. Or what you can basically do is that since you know that how they act, how they are basically acting on the fields, so from there you can
just compute
out
them.
Yeah. And the point is that since we do not expect any kind of mishap in this case, because this multiple soft graviton with 2 plus, so that does not, I think that does not suffer from any kind of ambiguity, like what is called, you can take simultaneous soft or consecutive soft. Because both are plus. So I think so this will be the algebra, and the good check of this is that we'll see that this is essentially the algebra which gives you the OP. So that's how we know that this.
So you're saying that the order of limit would, I mean, order which one goes
because
after,
both are plus actually. I think that is the.
And also they cannot be collinear or something. Is there some such?
No, so yeah, so I will come to that actually. So that's collinear thing is essentially the OP.
Okay, all right, thanks.
Because the things that you bring 2 point, so you have the fields on the sphere like phi, say phi1, z1, z1 bar, phi2, z2, z2 bar, and when you do the OP, you bring them close. Now, if you go back to the space-time picture, then this Z1 and Z2, those are the directions of motion of two massless particles, and they are so in the OP, they move in the same direction. So
the bulk interpretation of the OPE would be the collinear
yes,
soft particles. Okay.
Yeah.
Thanks.
Yeah. So that's what. Yeah.
Shamik, just one more.
Yeah.
So the J's, the SL2C guys,
right?
They are like space-time symmetry from the point of view of the ZZ bar space.
Yes.
From the point of view of the sphere, and the P's are internal symmetries, right? Is that
P's are kind of so actually, if you introduce, so if you look at the full Scry plus with all 3 U Z bar, then that is also a geometric symmetry. But if you want to confine this whole super translation thing to the sphere, then actually you have this addition. So it is a mixture in the sense that you have this multiplications by z bar or z to the power n plus 1, but this scaling dimension will also shift. So in that sense, it is actually somewhat internal, and also some powers of z's are there. So somewhat mixed. But the thing is that if you work on the full scribe class, then of course these are acting on the u, the retarded coordinate.
Right.
So their action is that zz bar goes to zz bar, so those things don't change. But then u shifts to u plus some function of z and z bar, and that function of z and z bar. So that by mode expansion, I have taken this to be of this form z to the power n plus 1 z bar and z to the power n plus 1. But the thing is that since we don't have the u here, so that there is a del u part which essentially is replaced by this change in h and h bar by half and half.
I see.
So yeah, so that's the thing. So if you write it as a vector field, then you will get f z z bar del u. Now that del u is essentially increasing the scaling dimension of phi by h and h bar by half and half. So that's the picture actually.
No worries. Thank you.
Okay. Yeah. So
one question, Shamik.
Yeah.
So can I, this algebra that you got of the J's and the P's, can I think of it as a contraction of current algebra with Virasoro algebra? Current algebra and Virasoro algebra in the large L limit or something like that?
Well, I don't know actually. So we can maybe discuss at the end what you really mean actually. So the Virasoro algebra, of course, you can get the Virasoro algebra from here, but we will not require that, at least for this class of scattering and amplitudes. But you can get it. Yeah, so you can have SL2C and SL2C bar current algebra. And if you look at the commutator of that, then they don't close, but they require the Virasoro and Virasoro bar. But I don't know if one can get it by contraction actually. I mean, I haven't thought about it actually. Yeah.
I mean, I just was thinking because P's commute, right? I mean, P's look like Virasoro, but they commute. So if you have the commutator is suppressed by some factor, then
yeah, these P's are the super translations. Yeah. So they also include the global space-time translations, like the 4 global space-time translations.
Yeah. Okay.
Yeah.
Yeah. Okay. Thank you.
Okay. Okay. So now we see that. So they actually form a closed algebra, which is nice. In fact, that makes it simpler, and that's what you get. Okay. Now let me go back. Now let us consider that why some set of scattering amplitudes are actually simple. So we'll talk about this MHV amplitudes. So now let's consider the tree level scattering amplitudes in GR. Okay, so they have this interesting property that if you take the look at the scattering of all plus or just one minus and raised plus, then those amplitudes are zero. And so the first non-zero scattering amplitudes are this MHV amplitudes of the form minus and the raised plus. So now let's call the set of all MHV amplitudes of this form as the MHV sector, and this set of amplitudes has the following property that there is no negative helicity soft graviton in the MHV sector. And the reason for this is that if I take a scattering amplitude of this form and make one negative helicity graviton soft, then what will happen is that because of the soft factorization, this amplitude will just so I have made one of the negative helicity soft, so that gives me soft factor into an amplitude of this form with just one negative. And we know from this that these amplitudes, if I just look at the GR, okay, so at the tree level GR, then this amplitude is not there, so that's why it is 0. So, and that is what I mean by the statement that there is no negative helicity soft graviton in the MHV sector. Okay, now these actually greatly simplifies things, because what we have seen that so I have not really talked the reason. I have basically focused, you can see that only on S plus, not, or say the S plus 1, because I want to do the MHV, and so I don't need the negative helicity soft graviton, and so all the algebra that I need is this, just the SL2C bar. So what I need is that this SL2C bar current algebra and the super translations of these forms, which we know also form a closed algebra. And so the point is that, so that's why we can, from the asymptotic symmetry point of view, so that's why the MHV amplitudes are simple because of this fact, because the symmetries actually simplify a lot because of this. And this is particularly true in GR in the tree level. Okay, so this is, so you can't take, so instead of GR, if you take something else, so you will not get this thing. Okay.
Sorry, Shamik, one question. Yeah. I mean, in the previous discussion, you applied these, I mean, you derived word identities for some correlation function of some phi's, right? You didn't specify what phi were.
Yeah, right.
So those phi's.
No, but the thing is that I looked at the correlation function of this S plus naught with a bunch of phi's, right? So there I did not talk about the S minus. That is just because of this thing, because I wanted to do the MHV amplitudes. So there I don't need the S minus actually.
Okay.
So that's the thing.
Fine. Thank you.
Yeah. So you have a G plus delta, but then the thing is that so that gives rise to this S plus, and similarly here also you have S plus 1, so you don't have S minus, so that's all we need actually. So that's why so I did not talk about the negative helicity, because in the MHV sector you don't have that. And now we can see that so now we get a closed algebra. So we have this JJ equal to J, PP therefore equal to 0, and this is what we have for JP, and that's all we need for the MHV sector. And so this is very special for GR actually. Okay, so the tree level scattering amplitude in GR. So in that sense, these are simplest, like GR is the simplest low energy, yeah, probably, or perhaps in that sort. Yeah. Okay, so now let me look at the OP. If we can construct the OP, so let's first start with.
Sorry. What did you mean by that? This happens only in GR. Do you mean with the Einstein-Hilbert term alone? I thought it was
Right.
Huh?
Yes.
You mean if you
So
had additional?
if you just have root GR, then only in that case, this the tree level S matrix has a property that all plus and all plus 1 minus is actually zero.
I see. So
But
if
if you have
add
R square or things like that, then you do not get it.
Oh, I didn't know this. Okay, thank you.
Yeah, so this is particularly true for the Einstein-Hilbert term actually.
I see. Thank you.
And that's why, so that's a very, I mean, that is because in the sense that from the, well, I mean, if you, for the time being, if you believe that there is something like flat space here, so in that case, this GR, actually just the root GR, so that has some special behavior, I mean, so it is somewhat special in that sense.
I see. Thank you.
Yeah. So I actually will now see that why this simplifies lies. So now let's get the OP of the two positive helicity gravitons, and that's if we compute this. So that's what we get actually. So this B is the beta function. And then we have some of the terms. So we have actually computed a lot of terms just to convince ourselves that this OPs actually makes sense on the sphere. And the thing is that I have just shown the first few terms because those are the ones we will need. But let me just state you that we also know actually other terms. Okay, so this is the OP which you can get from the MHV sector. And now let's see what we can do with this OP. So you can see that G plus gives you G plus, and you have this the descendants of G plus of the form. So these are the super translation descendants, and you have some things like that. But we will now see that these descendants are not actually independent. So that's where the primary descendants or the null state thing will come into play. But let me just first show you that why they are not independent, and then we can go back to the more algebraic approach. Okay. So now let me go this thing. So now what we do is that we have this G, we know what this G plus ZZ bar and G plus delta 1 Z1 bar. So this G plus delta 1 Z1 bar could be one of the phi's which we had, like phi HH bar, ZZ bar. So one of those phi's is now this G plus delta 1 Z1 bar. Okay. And now what we do is that we now take the subleading conformal soft limit on this G plus delta ZZ bar, which you know has this form. Now, if I take the subleading conformal soft limit on this G plus delta ZZ bar, then what I get is, if one can easily compute this, what you get is this. So this OP which we have, once we do this, delta going to 0 times delta G plus delta ZZ bar, we get back this. But now let's see. But the point is that this is also given by the subleading soft graviton theorem, because this limit delta going to 0 delta times G plus delta ZZ bar. So that is essentially the S plus S plus 1 ZZ bar, I mean, which we talked about here. So let me just show you this thing. So this is the thing, like S plus 1 ZZ bar is the limit delta going to 0 delta times G plus delta ZZ bar. And we know that now once we replace this phi with this G plus delta 1 Z1 Z1 bar. So that has to be of this form. So now if I compare, so I should, from the subleading soft graviton theorem, I should get back this. Now if I compare this 46 and 47, what I get is these two equations. So one is delta 1 minus 2, p minus 2 comma 0, j plus delta, and this. So this is the reason I said that the descendants which we have here, they are not actually independent, and that is just because of this. So this g plus, so we have these relationships between the descendants. And the thing is that since these things hold for any value of the scaling dimension delta and delta 1, what we can do is that we can simplify life just by shifting this delta 1 going to delta 1 plus 1, and what we get are these things. So these are the things which basically come out of the OP and the, so that's what we get. And now you can see these look exactly like what null state decoupling will look like. So you get this J1 minus 1. So these are the SL2C bar, and then you get the P minus 2 comma 0, which are the super translation, and you get also this second one, which is actually the more important one. So yeah, this one. Yeah.
This is probably like the key equation. Right?
Yeah.
I just want to make sure I understand. So I'm sorry, I haven't followed properly, but
no. Yeah, just go ahead.
You did a calculation, one using some subleading soft graviton theorem, and the second one using something else. Both had to agree. That was what I understood. What were the two pieces that? Sorry, tell me again. What was the physics for getting this? In bulk terms, if possible, what was the physics for getting that you add soft gravitons in a particular way and you get 0?
Right. So the thing is that what you do is that you take the, you compute the OP of two hard gravitons, which are of, and then you get this form, this G plus delta ZZ bar, G plus delta 1 Z1 Z1 bar. So that has this form. So is that fine?
And this came even though the two gravitons were hard, because where did the information come from for this equation?
Yeah. So this we have obtained from the scattering amplitudes in GR.
So it's just by knowing the explicit form of the scattering amplitude.
Yes. So, but now actually I will show that how to do that if you don't know what is the explicitity. But so this is done well. So I'm just I could have started just purely algebraically, but I did not want to show you in that way because that's how we did not do it actually to start with. But this you obtain from the this you obtain from the explicit expression for the scattering amplitudes in GR.
Okay, so far the logic is that given the explicit expression for the GR scattering amplitude, this combination of descendants happens to vanish.
Yeah, this, yeah. So first from there we construct the OP, because it is not since this is not a standard theory, it is not clear that the OP will actually exist, but we find that it does actually. So that's what we do, the first step. And now the second thing is that now the point is that this OP has to be consistent with the subleading soft factorization, and that gives me these things.
I see. So you take the answer when two hard gravitons come together from the explicit answer,
and then you make one of them soft, and then you match it with the soft here.
And then it has to agree with general expectations.
And, exactly. And
you get something. But the key information so far is coming from the explicit form of the S matrix.
Yeah, but you don't. That's what I'll do now. Actually.
Please, thank you.
Shamik, one question.
Yeah.
In the OP, apart from G, wouldn't you expect any other operators also?
No,
Just
so
like any
this is just GR, right? So you don't have anything else other than G. So if you include some scalar fields or something, then you can get those things. But this is just
no. But how about two graviton states, so on?
No, but if you just have gravitons, then you can only get G, right, on the right item side of the OP.
Okay. Okay.
So it is just
sorry.
root GR actually. Yeah. So you don't have anything else.
Sorry, maybe I'm not getting how you're thinking, but if you have two particles, two gravitons, and then they could produce multiple gravitons also.
Yeah,
so
but
that
does not contribute to the OP actually. So
yes, why is that?
Yeah, so you can show that it is these are just the three vertex which contributes to the OP. So you can think of like this actually, that two come together and one of them goes out, which is the G on the right hand side.
Okay, but why is it that multiple gravitons don't contribute? Because
So
the root GR interaction can give rise to a lot of
yeah, but the surprising fact is that at least for this class of scattering amplitude, all those things they are just basically determined by the three graviton amplitude.
But what about contact?
No, but those don't contribute to the OP actually, so that you can show. So yeah, I think.
So this is not a symmetry reason. That's something that you have to compute and show explicitly, or is there a quick thing? I mean, is there a way to see it more abstractly in symmetries?
Within symmetries, well, if you just assume that the OP is there, so what you can do is that you can assume that the OP exists.
With other stuff also, other GG kind of stuff also.
No. But the thing is that in the OP, you like on the right hand side, you can have only a single field, and that can only be G, right? Because you don't have any other field in the.
But field, I mean, I'm thinking of this as conform field theory, right?
Right.
So can I not think of G as an operator, a single single operator, and then there could be a composite operator with GG.
Something.
Well, so that okay, yeah, I don't know. Like yeah, so we can talk about that maybe. But
let's say normal ordered kind of guy with a lot of G's and so on.
Well, normal ordered with a lot of G's. You mean the composites of G?
Yeah. I'm just asking because in conform field theory of phi, for example,
could appear
interacting theory.
Those could appear, but let's assume that they don't. So for the time being, okay. So I don't know of any abstract way to see that why they will not.
Maybe they are suppressed or something.
Yeah, that could be actually. So this is the leading OP in the sense that this is 1 over Z minus Z1, and then you have all these subleading terms.
Okay, fine.
Yeah. Yeah, so these are the key equations which we need. And the thing is that, so now let me write the OP in terms of the linearly independent descendants, and what you get is this. Okay, so you have J0 minus 1 and P minus 2 minus 1. Okay, now so the point is that, so we can see that as expected, because what we saw here, that why these MHV amplitudes are special, because they don't have a year. So we saw that we expect that in the MHV sector, we have only the SL2C bar and these super translations of this form. And the point is that that is what we exactly see here, because we have these J's which are the SL2C bar, and we have these P's which are the super translations. Okay, now the most important fact, of course, is the fact which Miraz was asking, and this is the answer to that. So I will not show the algebra, but the point is that these OP coefficients which we have here, these subleading OP coefficients, they can be obtained by demanding that both sides transform in the same way under the extended symmetry algebra. So these OP coefficients like these, so or these like P minus 2 comma 0, so they are obtained in that way. Okay, so you don't really need the explicit expression for the scattering amplitude in GR in order to get this, but we did it in that way because we were not even sure that reasonable, well, we had to check with what we do actually. And the most important point is that this beta function, this beta of delta minus 1, delta 1 minus 1, can be obtained from the differential equations, which we now write down. Okay.
Shamik, can I ask?
Yeah.
In equation 52. So the right hand side apparently has something to do with GR itself. That is to say, to the Einstein action, or so suppose you add some term to the Einstein action so that the 3-point coupling changes.
Yeah.
Okay, so then the right hand side will change. But are you
saying that also get some extra terms actually?
Right. So are you saying that the left hand side will also change? Left hand side has to do with symmetries, I thought.
No, left hand side is just the expression for the OP, right? G plus delta.
Right. So I thought that the left hand side does not care about.
No, the point is that what is happening is this actually, right? So you mean the right hand side, right? Not the.
I mean the right hand side will change, but it seems that the left hand side will not.
Well, so this is a different. So this G plus delta ZZ bar, G plus delta 1 Z1 bar. Now this better change because this particular thing will break down because of this thing. So the reason we can write all the descendant, the OP in terms of the descendants, the SL2C bar and the super translation descendants is because of this particular fact that we don't have any negative helicity soft graviton in this sector, and that is true only for the GR with root GR in that sense.
I see.
So once you add extra terms, so this thing will not hold, and the symmetry algebra will be much bigger.
I see.
So there you will not just get SL2C bar, you will also get an SL2C algebra. And then I think you also have to take into account the super translations will also change, and then you get an extremely big algebra, and so that's why since the symmetry algebra will change, we expect the right hand side to change actually.
Right.
So
okay, thank you.
So this thing
to make sure, the S matrix from Einstein gravity is the unique S matrix that preserves all the symmetries you are imposing. Is this right?
Exactly.
So the same, you could use that symmetry algebra to solve for it, presumably.
Yes. So that's what now I will do.
Thank you.
Yeah. So that's
sorry,
what
just to repeat what Shiraz said. So from this symmetry algebra, you can derive root GR. Is that?
Well, not root GR, but all the scattering amplitudes of this form, the MHV ones. So in the sense that if you just impose this SL2C bar and super translations of this form like Pn-1 and Pn0, and then if you compute a scattering amplitude of this form using that, then that will essentially give you the scattering amplitude for root GR. But yeah, but how to translate that into root GR? Of course, yeah, I think from the S matrix you could get that. But the point is that yeah, that is essentially the true actually.
Okay, thank you.
So that is what I will now actually show. Yeah. So now actually let us go just do it here. So we have this decouplings. So these are this so in terms of J and P delta. Now so if I insert these equations inside an MHV S matrix, then what we get is this, and these are the so this curly J1 minus 1, so that has this form, and then the most important equation is this. So this will be solved by all the G plus. So this is L minus 1 del del Z and L bar minus 1 del del Z bar. And one thing you can see is that this equation, this differential equation, which is 55, so that has no holomorphic factorization. We don't even expect that because the underlying symmetry algebra is not holomorphically factorized. But these differential equations are all known very explicitly, and these have this form. And so this is the standard, roughly the way we get these things in 2D CFT. So now actually what we get is that, so for an endpoint MHV amplitude, which contains two negative helicity gravitons, so that satisfies n minus 2 the differential equations of this form, because you have n minus 2 for positive helicity gravitons. Now, since these things like, since we don't really have a kind of axiomatic understanding of what the dual theory in this case is, so we actually checked that these things really hold if we take the explicit expression, and they do actually. For example, you can take this simpler one, so that can be checked for any endpoint scattering amplitude, and the more complicated one, and which is the one which is the more useful one, is well, I mean, not useful, but the thing is that this one is more fundamental in some sense. So this can be checked. This has been checked up to 5-point amplitude. So now we will see exactly what does, and go from the I was saying that how we can get this from the extended symmetry algebra that we have. Okay, so now let's look at one of the simpler ones. Say for example this one. So we have this phi z bar equal to J1 minus 1 P minus 1 minus 1 minus delta acting on G plus delta is actually 0. Now the thing is that, now let's just talk about it from a purely algebraic point of view. So in that way, what we will say is that this equation, so that makes sense only if this phi z bar, this particular state, so that's a primary under the extended local symmetry algebra. So in fact, we can obtain the state phi by demanding that it is a primary under the extended algebra, and that's what we will do now. So now, so let's start with the state. Let's call it phi1, which is one of the state, which is j1 minus 1 p minus 1 minus 1 g plus delta, which is the first state. Now, what one can easily check is that the only other state with the same scaling dimension is phi2, which is this one, which is p minus 2 comma 0 g plus delta. And so what we do now is that we take a linear combination of these two states of this form phi1 plus c phi2, and c is the unknown coefficient that we have to get. So this c we should get c to be minus delta minus 1. Okay, so now so what one can easily show is that this phi1, so this state and this, so this state and this state, this phi1 and phi2, they are individually primaries under the Poincare group. So that means that this capital L1 phi I, L1 bar phi I, and this P0 minus 1 P minus 0 acting on phi I is 0 for I equal to I equal to 1 and 2. So the good thing about this is that you can see that this coefficient C, this can't be determined using the global Poincare symmetry, and what we need to get this C is the local symmetries. So we just use them. So we use this condition that this phi has to be a primary under the SL2C bar. So JAN acting on phi, so JAN will kill this state phi for all n greater than or equal to 1. And the point is that now you can use the fact that this G plus delta is a primary under the extended algebra, and you can use these computators like this, the computators between J and P to show that both J1n and J0n, so that acting on phi is 0 for all n greater than or equal to 1. So we are left with just this J minus 1n for n greater than or equal to 1. So now let's apply the first one, which is J minus 1, and and if I apply this, what I get is this. Okay, C plus delta minus 1 acting on this. So that gives me this. So that determines C, and C we get is minus delta minus 1, which is exactly the answer which we are looking for. So this minus delta minus 1 was the C. Okay, so we should have obtained this C, and C turns out to be this by applying. So here you can see that we have used the local SL2C bar transformation, and the important point is that the local symmetry is required. You can't do it using the Poincare algebra. Okay, so these things are actually, these local symmetries are useful. And so once you get C, you can just say that, well, with this value of C, so I get a primary descendant, and I can consistently set that to 0, and that gives me this equation. And the point is that you can actually do the same thing for this second one, which is this, and it turns out that you exactly get, so you start with this, you take something like this, L minus 1 P minus 1 minus 1, and then you add C1 C2 C3, and those C1 C2 C3, those can be obtained from this SL2C bar and the super translation. So this is an example where we can see that this singular local asymptotic symmetry transformations, they actually determine a class of scattering amplitudes in GR, which are these MHV. Okay. Okay, so now the point is that it is not well. So since the point is that it is here that we have written down these differential equations on the sphere, but the point is that since it's an integral transform, we can now translate these differential equations to the standard Fock space scattering amplitude, and this is what it looks like. So you have n-2. So this is the standard S matrix, not the main transformation of that. And these differential operators now have this form. Since we have come back to our this Fock space, so the omegas are there, and you can see that you get n-2 the differential equations, which, well, I think perhaps only in principle you can solve to get this thing. And the point is that one of the reasons I actually said that, well, so I wrote down this equation in the Fock space is that perhaps there is a way to get all these things in the Fock space. So that is one thing that we want to do actually. But the thing is that the existence of these things, they tell us that even if we go to the Fock space, because the S matrix, so I mean it's just a basis transformation. Now that basis transformation is extremely useful, and it has lots of like exceptionally good things. I mean, it simplifies things, but perhaps in principle you could do this thing. So if you don't believe in the celestial sphere, you should still take this. You can still take this as a take home here, that the standard S matrices also get constrained in this way. And the point is that, so now let me just flash one of these things that I have talked about the gravitons, but you can do the same thing for the gluons. And for the gluons, you get equations like this. So this is very similar to the Nisnik-Zaplotchikov equation. In fact, if you look at the first two terms, that has almost the same form except this HI. The CA is the quadratic Casimir in the adjoint representation. These T's are the SUN Lie algebra generators. But on top of that, you also have an extra third term, which comes from the subleading soft gluon factorization. So that's the thing actually, and you can get the MHV amplitude for the gluons in this way, and you can also get it in a purely algebraic way. But the point is that it turns out that gluons are much more complicated than gravitons actually, and so but still you can get this thing. And yeah, so
sorry, one question.
Yeah.
I mean, when you consider 4 points, already there is some issue that was emphasized by, I think, at least Strominger talked about it at strings. So when you consider 4 points on the celestial sphere, a priori in conform field theory, it could be a function of 2 cross ratios, right?
Yeah.
But when you have scattering process, then isn't it the case that it should be localized on Z equal to Z bar slice?
Yeah, but that's not an issue, because you can see that those even 4-point function will solve these things actually. Yeah. So that is already implied, like it has to. So delta, if you do it for the 4-point function, then delta Z minus Z bar. I mean by Z, Z is the cross ratio of the 4 points on the sphere. and z bar is the complex conjugate. So you have a delta function of z minus z bar, but you can still do it.
So I do see it from here. I'm supposed to see it from this equation that this shall support only on this.
No, so that is of course no. So that is determined by the global space-time translation. So that is already implied here in the sense.
Oh, I see. That's taken here.
Yeah. So that is already part of this because the symmetries are all there. So as long as it is there, so that fact that the 4 points have to lie on the equator, so that constraint for the 4-point function is already inside this.
So now, what does this mean for the Kuznets-Zambrano-Chekhov type equation? I mean, that equation is usually an equation, where these constraint is not obeyed. So now we want to impose that constraint on top of this.
Yeah. Okay. So well, it closely resembles this, but it is not exactly this, and that's why like you get, for example, you have a third term, okay, which comes from the subleading soft gluon factorization, and then also this you can see this hi. So this factor is not there in the standard KZ type here. So this hi is the scaling dimension of say GHI. So yeah, so that's why. So it is not exactly a correlation function of a WZW, and that is taken care of by these extra things actually. So it looks like if you this here CA by 2 del del Zi, and this factor, this TAI TAZ by J by Zi minus J, yeah. So these factors are same. You can have a K also, which in this case actually turns out to be Z. So that is the thing. But it is not exactly. I mean, it can't be the same because it is not exactly a Wiener-Witten on the here. And that is this is essentially that. Okay, so I'm just at the end, so we can see. Yeah, so we have the point is that what I will say is that since so these scattering. So what I want to actually emphasize is that the existence of the OP on the sphere. So that means that the subleading terms in the collinear expansion have a universal structure which is determined by some symmetry. And the thing is that this universal structure plus the soft theorem that should be extremely constraining. And actually, I think, well, I mean, it will be nice to know like how to combine these things with the more conventional ways of doing the S-matrix bootstrap. And also the point is that the usual S-matrix bootstrap, of course, if it's a massive theory, then it's extremely well defined. But once you have massless things in the exchange or in the external legs, it is somewhat, I think, yeah, some of these things, the structure in the metal stamp plane, these things become more not so useful perhaps. So this could be, if we combine these things, probably that can give us a different type of things and useful thing actually. Yeah, so I just stop here. Yeah.
Thank you very much, Shamik, for a very nice talk. Let's all unmute and thank Shamik. Questions?
Shamik, how is the symmetry algebra structure that you talked about? How is it affected by loop diagrams?
So that is so actually there will be infrared divergences, and that will I think the leading soft theorem will not change, but this subleading soft theorem will change. So by subleading this thing actually, so if you look at this, so this gets some additional contributions. Okay, yeah. Now, how, I mean, what is the exact way of taking that into account at the level of symmetry algebra? So that actually something which, yeah, we didn't really look at that. Yeah, but this will change actually. This can get certain extra things coming from the infrared divergence.
Okay. And one more sort of related, similar question. If you look at just at tree level diagrams, but in string theory, presumably the symmetry algebra is not correct.
Yeah, but because then you have to get the negative helicity here also.
Yes.
Because yeah, right. In the symmetry algebra is much bigger.
Right. And I was wondering whether there's some deformation of this algebra that applies to the string theory amplitude, because that's such a
it should actually, because the thing is that but it's just that for the tree level string theory, so that will be that algebra will be much bigger, and we are actually in fact trying to do that, like how to, because if I have both I mean not just the string theory, but if I go beyond the MHV amplitudes in GR, we will need that bigger algebra. But the thing is that, yeah, so, but that is where things become more, actually. So this is sort of the simplest thing that one can do.
Thank you.
But what I think what was somewhat surprising, like, well, I mean, it's probably expected that once I fix this SL2C bar current algebra and for translation, the scattering amplitude that we get, they have to be the scattering amplitude of GR actually. So in that sense, yeah, it was quite unexpected, yeah, to some extent. Yeah.
One more question. At some point in your talk, you said that you were looking at the OP of hard gravitons.
Right.
Then you first looked at the explicit answer to check that this OP actually made sense.
Right. No, see, yeah, so we checked at the level of amplitude, because when we started these things, we were not sure that the OPs will actually exist. Okay. Because we don't have any axiomatic understanding of these things, right?
Right. So I was wondering, I wanted to ask whether this existence of the OP is a property just of this MHV amplitude, or you think it's true for just all tree level gravitons scattering?
Actually, this first term, so if you look at this first term, this z bar minus z bar 1 by z minus z1 p minus 1 minus 1, and so that exists for all scattering amplitude, including string theory ones. Okay, so that factorization, so that is a now higher order terms. Now that is a very, yeah, so that is something like why it should just stop existing actually.
So you expect it to exist?
Just expected, yeah, but it has to be done, because now the problem of this is that if you go beyond the MHV, the symmetry algebra becomes much more complicated, and so that is the thing that first we have to actually understand.
But just for the question of whether the OP exists, couldn't you just take the 4 graviton scattering amplitude, which is explicitly known, and just check that outside the MHV set?
Well, the 4 graviton scattering amplitude, but that is, you mean the minus plus plus?
Yes.
But that is also an MHV amplitude, right?
I see. Sorry. Yeah. So 4 gravitons has no information.
Yeah. So it starts at 6 actually.
Yeah, 6. I see.
So that is where because the thing is that, So we don't know. So like we don't have any axiomatic understanding of that. So we should start from the 6. So it is minus and plus plus plus. So that's at the first amplitude start. But then the problem is that these expressions are explicitly known, but they are so complicated actually. But I hope we will actually do something from there actually. So once we know that so that is the thing.
Thank you.
Yeah.
So Shamik, sorry, just to understand, very clearly what was done. So first of all, the soft theorem kind of gave you this thing where you have a soft insertion, and that was equal to a particular differential operator acting on this hard part, right? And but finally, finally, what you wanted was just some differential equation obeyed by the hard part, right?
Right.
And how was that soft? The equation had as a word identity both the soft insertion and this differential operator. And how did you get rid of it? Then using the OP, right? Somehow, can you show again how
this soft part? So so that is essentially these three J's, these J1 and D. So that becomes so just you can think of that as it's the standard way we think of them in CFT or in two-dimensional conformal field theories. And then the point is that since the reason was that we also have to convince ourselves that what we are doing is right. So we computed this OP, this G plus two hard gravitons from the trading amplitude. From there we got this, and then what we found was that this is not as it stands. It is not consistent with the subleading soft factorization or the word identities of the J's. Now, if we require them, if we require the OP to be consistent with the subleading soft factorization or the word identities of J, then that gives us these two differential equations. But
sorry, can I understand this a little better? So what is, so in order to get 48, you are using 46 and 47, right?
Yeah, right.
So 46 is the OP limit that you had, and then in this soft limit you get this.
So
and then you are matching it with what? Yeah.
No, I start with 44. So 44 is G plus, and then I take the subleading conformal it on that. I get this. Now, this right hand side of the 46.
Oh, right. Okay, I see. I understand.
Left hand side of the 46 must be the same as what we know from the subleading soft factorization.
Okay.
And then that gives us this. But then at the end, once you are reasonably convinced that these things make sense, then you can actually go back to the purely algebraic way, and that also gives you this thing. But we could have just started with the algebraic way, but I mean that's not at this stage. I mean that's not what we want to do actually, because I mean we have to make sure that these things really work.
And on the last slide, you talked about some sort of a bootstrap. Like what kind of bootstrap did you have in mind?
No. So these are bootstrapping the massless. So if you have external,
but this is a tree-level structure so far, right?
This is a tree-level structure. At the loop level, you have this infrared divergence issue, but perhaps probably one can, I don't know. But if you just also look at not in 4, suppose you look at 6 dimensions or something like that, or 10 dimensions.
Okay.
And there actually one could see actually, I mean how, because these
so now fix the tree level matrix, you're saying?
Tree level F matrix, that this particular class of MHV amplitudes, so though in GR, so those are completely fixed by the asymptotic symmetries. But the point is that if you come now like put some constraints on the, say, the coupling of a particular term in the Lagrangian, like a 3-point function, something like, I mean, I think some such things, if you combine this symmetry thing with that, because once you have massless things, massless fields, so you can't really ignore these things, right? So that's what I'm saying.
But if you modify the Lagrangian, then your symmetry is also supposed to change, right? Because you or well, not, or you know,
it will just be bigger in that sense.
Okay.
But the soft, as long as the soft factorizations are there, those actually is so that should be fine. So the soft factorization holds.
So if you consider, for example, Einstein gravity plus, say, Cosmone gravity, both your 46 and 47 changes, or just one of them changes?
Okay, let me just see.
I might be asking something
46, 47. Okay, so if you, instead of the, so suppose you have root gr plus some cos term, okay, then the point is that the right hand side of 45 should also change.
Okay.
Because the point is that the symmetry algebra now it's not the same as the SL2C bar plus these super translations of these form, because the point is that now the symmetry algebra is much bigger.
Okay.
So it's just purely from the algebraic point of view, you can see that this right hand side of 45, and as a result of that, the right hand side of 46 also has to change.
Yes.
But 47 right hand side will not change as long as you don't consider loops.
No,
because the 40.
I'm just considering tree level diagrams with
Yeah.
R and R.
Then the right hand side of 47 will not change, because this is 40. The right hand side of 47 is essentially the subleading soft factorization, and that will hold for any tree level in this. So the right hand side of 47 is essentially this factorization, right? This S1 plus ZZ bar acting on this is this. Now this will hold not just in tree level GR, but you can add terms like that. But what will change is actually the right hand side of 45, 46, and also 45, because these you have much more. The symmetry group is much bigger now.
Why would the symmetry group be bigger?
Because so in the MHV sector, you have only S1 plus or S0 plus. But the point is that if you go beyond the MHV sector, you have both S plus minus 1 and S plus minus 0. So you have SL2C constant algebra and SL2C bar constant algebra. So both the algebras are there. So is it
and this by but you mean global? You mean super? Okay.
So the fact is that, so you get I think
I'm kind of confused because you're talking about the subleading, and subleading was due to the the diffeomorphisms of S2 and similarly.
Right. But
those we don't even know if they'll be there if you have these higher order corrections, right?
Well, I think the tree level, this subleading soft theorem still holds, right? With all the, if I have a root gr plus some cos term, I think this Cachazo-Strominger, so that does not get.
I don't know. I'm asking.
No, I think the tree level, this subleading soft factorization, not for the gluons, but for the gravitons actually. So that will not change. I think that remains unchanged. The only thing is that, yeah, also the scattering amplitudes will be more complicated because there is no notion of the MHV amplitude in that case, because all plus will also give you some non-zero answer, and that would mean that the from the holographic perspective, the symmetry algebra, which gives you the scattering amplitude, that symmetry algebra will change, and that will result in a different scattering amplitude, which is of course we expect, because now the theory, the bulk theory has changed. So yeah.
Also, in the conclusion, you said that some question like where is unitarity in this?
Yeah, so that is an algebraic. Actually, that's a nice, actually algebraic question. That you have all these descendants, primaries, and all these things. Basically, what I meant was that, well, I mean, is there, can one construct some? So we talked about the primary descendants. But these are, well, we can't really talk about a null state because we have not introduced any notion of a norm here, right? Like,
yes.
So you can't really say that, well, this state is the norm of this state is actually 0, and so yeah, so that's what I meant. I mean, is there a useful notion of, I mean, can one introduce a norm? And yeah, so that's what I meant.
Sorry, just to follow up on that.
Yeah.
I mean, S matrices normally have obey a clear unitarity relationship when you go to loop order, namely Kutkowski's rules. Right. So there is a clear consequence of unitarity once you go to loop order, because then
yeah.
But it's not so clear that there is a clear manifestation of unitarity at tree level, except for the fact that poles have to come with positive residues.
Right. No, so I was asking more a group theory question, in the sense that we have all these algebras like this SL2C bar coefficient algebra and these descendants and all these things, but can one introduce a notion of, I mean, like say some state or operator correspondence? You introduce a Hilbert space, you construct, I mean, with a norm, and then you can, I mean, that sort of thing actually. Yeah.
I understand, but there should also be some translation of space-time unitarity. You mean this Kutkowski's rules into this language?
Yeah. So the thing which you said actually, that the residues at the poles
are related to 3-point functions.
Yeah. So actually, I was just thinking that if one could do all those things just from purely algebraic perspective, actually. I mean, that may not be necessary, but it will just be good to actually have such description. But one thing is for sure, that this symmetry algebra, this SL2C bar plus this super translation, so that determines the MHV amplitude, and that gives you the answer for the GR. So in that sense, that particular sector is like a solvable sector of the dual actually. So since there is some solvable sector, maybe that, I mean, there is a kind of dual.
Yeah, so it sounds very nice. Just one more question. I mean, it's a bit vague, but suppose one were to extend this to loops. Then,
right.
Then Kutkowski's rules, if translated to this Mellin transformed basis,
right,
would give you some nonlinear equation for your correlation functions.
Right.
I was wondering whether it would be a useful idea just to translate Kutkowski's rules to this Mellin space basis and see whether it looks like a natural structure.
Yeah, I think that would be extremely interesting actually. I mean, if one can interpret this in a nice way. Yeah, but it has to be done. I think no one has done this thing actually.
Okay.
Yeah.
Thank you.
Yeah, but the thing is that, I mean, this will be important because, yeah, I mean, without unitarity, actually, it is very, yeah, I mean, it doesn't make, yeah. But I don't think anybody has actually done that. I mean, it would be interesting to do it actually. Actually, loop amplitudes have been recently computed. The main transformation of that, but I don't think they have looked at this particular question. But I don't think. Yeah.
Any more questions? If not, let's thank Shamik for a very nice talk.